Hi, in this video I will complete the single-step clock circuit as well as the circuit to select between the timer clock, the automated one, and the single step. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, so let's look at this single-step switch here. In order to hook this up, I want to create a monostable timer circuit. And that timer circuit has one stable state where the output is going to be at a logic low state. And then when I push this button, it's going to rise to the logic high state, stay there for a period of time, and return back to the logic low state. Effectively a single clock tick. To hook this up, and I will put the schematic up here, or the wire up diagram up here for a monostable operation circuit. We want to tie the reset line high. That's going to be pin 4. So pin 4 is going to be tied to 5 volts. And then as we look at this circuit diagram, or how to wire up the one of the 555 timers, we've got 5 volts connected to discharge and threshold being pins 1 and 2, and then connected through a capacitor to ground. So pins 1 and 2 get tied together, and that's done very simply like that. Then there is a resistor and a capacitor. And what I have here, I've scavenged off of other projects. So what I have here is I have a 1 million ohm resistor that's going to be connected from 5 volts to the discharge pin. And then I have a 0.01, that's actually not the correct one. So I have a 0.1 microfarad capacitor, and that's going to be connected to ground. So that's going to be off. I'm going to check my pinning here, my threshold to ground. So that's there. And then the resistor gets connected from 5 volts to the discharge pin, pin 1. Okay, so that wires that up. Now the control line, this is where the 0.01 microfarad capacitor comes in. The control line 3 is connected to ground using that capacitor. And wiggle that in here. There we go. 2 capacitors side by side. Now, that leaves our trigger and our output. Our output is pin 5. And our output's going to get wired over here to one of the LEDs through a 220 ohm resistor, red, brown. Yeah, red, brown. 220 ohm resistor, and that's wired to ground there. And then now we have to worry about the trigger. Now, unfortunately, the way that this diagram shows, it shows the input being a high trigger. But knowing a little bit about the 555 timer and how it works, the trigger actually is hooked up to a comparator through a voltage divider, so that at 1/3 of the voltage in, or 1/3 of 5 volts, 1.67 volts, if the line drops below the trigger, so the trigger input is below 1.67 volts, then it is actually going to trigger the 555 timer to go through a cycle. And so rather than tying this such that when I push the button it is tied to ground, I'm going to tie it high through a pull-up resistor. And this is a 1000 ohm pull-up resistor. And that's going into pin 6. Then what I will do is I will take that over here to the switch and then connect the other side of the switch. I can do it here or I can do it here. The other side of the switch to ground. Now what that does is that it's going to provide 5 volts through the resistor to my trigger pin. And then when I push the button, it's actually going to drain, bring it to 0 volts. It's not going to short that connection because I've got the resistor here to limit the current flow. But it will bring it down to 0 volts, and that should then turn on the light. And it should stay on for a short period of time and then turn back off. So let me grab my power here. I've got it wound around a bunch of stuff over here. Grab my power, plug it in, and then take and plug in my clock. And then when I push, it stays on and then turns off. If I want it to stay on for a longer period of time, I can use a larger resistor. And let me demonstrate that. Excuse me while I reach for a resistor here. These are 5.1 million ohm resistors. So if I pull this 1 million ohm resistor out and I replace it with a 5.1 million ohm resistor that's tied to 5 volts, I'm expecting it to stay longer, and it's not. That's fun. I love it when things work right the first time. Maybe my capacitor. Let me grab a different one out of my supplies over here. And you can tell that I am obviously not pre-doing all of this work so that I can transfer it from one working breadboard to another breadboard. Yes, that is 10 times the size capacitor, and therefore I get a much longer delay. Now if I put the 1 million ohm resistor back in, again tied to 5 volts. Anyway, what I was saying is that you can tell I don't pre-work any of this circuitry just so that I have a known working circuit before I put it on camera. So the 5 million ohm resistor gives me a nice long delay, but it's a little bit longer than I would like because I don't want to have to wait that long. So if I put the 0.1 microfarad capacitor in with a 5 million ohm resistor, I'm trying to get it to stay on longer than I'm tapping it, but I'm not getting what looks like any double taps on it, so that's good. I am going to come back, and I think I'm going to put a Oscilloscope up to this, and I'll do this in this video. But what I do want to do is I want to spend a moment here, because if I tie this to the right side, so this is the automated clock, to the right side of that switch, and I tie this line to the left side of the switch, the tap in the middle now contains the clock depending on which direction it's actually pointing. So I'm going to tap the middle of the switch here, my big old club hands, And I'm going to come out here to this last LED, green LED, and I will put a 220 ohm resistor on that. And that'll be tied to ground, current limiting resistor. So if I push that, I now have two LEDs that light up. My switch is all the way to the left. And if I move it to the right, then I am getting the automated clock. Let's see if I can move those wires out of the way. To the left, I get the left LED here. So as I push the button, I get the debounced clock. And to the right, I get the automated clock. And if I speed it up, the clock itself speeds up as well. Now I'm going to need to invert this clock. And I also don't like the idea of having two LEDs being driven by the same signal off of a single IC. I'd rather buffer that somehow. So at some point I'm going to have to figure out how I'm going to A, invert the signal, and B, buffer the output of the signal such that the buffered output drives the LEDs, not the clock signal itself driving the LEDs. And of course I want to clean this up a little bit so that I actually have something that looks a little bit neater. So I will go through that cleanup now. I did also get a mailbag today, and I kind of want to go through the contents of what I received. I got these larger audio potentiometers, variable resistors, that have a much smoother action. Very easy to turn the dial here. It goes almost all the way around. Or let's see here, is it 50? Yeah, almost all the way around, about 300 degrees. And those, however, are not going to fit into a breadboard. So what I figured I might do is grab a pin header like this. And they do slip right in here. So and it just so happens that it fits every other pin. So pin 1, pin 3, and pin 5 all sit into the connections here. So if I solder this together, without bridging anything, of course, I should be able to snap off these last 3 pins here and then plug this straight into the breadboard and use this for my connections rather than that other potentiometer, which was giving me all kinds of problems turning it. So that'll come up in a future video. I will make that quick modification. I also got some desoldering wick, and that'll be good for my future endeavors with surface mount. I picked up a couple of, let's do it right side up here, 100 megahertz. Try to get this without the glare. 100 megahertz crystal oscillators. And so my intent is to later, at some point down the road, I'm not going to do it right away, I'm going to augment this timer circuit, this clock circuit, so that I can actually get much higher clock rates. There's also a VGA circuit or VGA standard that runs at something I can divide this 100 megahertz crystal to. So I'm going to work on getting 2 of those tied in the future, but I wanted to get them before they weren't available anymore. So those are set for a future video, quite a bit ways down the road. I did get a chisel tip, and I gotta be honest, I'm quite disappointed in this. It looks like it doesn't really have much of a chisel tip. When I see or hear chisel, I'm thinking a nice sharp edge. I do have a wood shop, and I do spend time down there. And I don't know if you can see just that little tip. It's very small. It doesn't look like it's chiseled down very far. But it does have somewhat of a flat edge on it, so we'll have to see how this works. I don't believe that's going to work as well as I want it to, but we'll see. I did get some strip boards, and now the intent here is to put headers onto the strip boards, basically right next to each other, so that the amount of copper that's in between each one of those is very reduced, and I don't have to worry about bleeding too much away from that. And then I got some pin headers as well. Let me pull those over here. So these pin headers are 8 wide, and they will plug straight into the strip board here, like so. I'll solder them in. Obviously, they'll go in from the other side, but I'll solder those in, and then you can see how this then becomes buses that I will be playing with later. There is enough room that I can put 2 of them side by side. And so I'll be able to get 16 across. Even with the holes here, I can work my way up from that. I'm not going to have that many connections into this. So there's actually 19 rows of strip, and so I'll be using 16 of those. And then I got some dip switches, which are through hole mount. So this, I have been very disappointed in dip switches in the past that don't actually fit into a breadboard. So these will pop right into a breadboard and actually will stay, allowing me to flip things on and off without actually having to worry about pulling the switch itself off the breadboard. So that sits pretty securely. And so I've got several of those that I will be using, such as cutting down or as a divider for the frequency of these clocks, or these oscillators, crystal oscillators. So again, all of this will be coming up in a future video. But that was my mailbag today, and it was like Christmas. Okay. Couple of thoughts here. First of all, I apologize for not keeping that in view. I'm going to have to figure out a way to get better at that. I'm not exactly sure how I'm going to deal with that in editing, if I'm going to just cut it or try to run through it. But I do know that I missed several components, or at least it was sliding off closer to me as I was doing the work. I'm using green lines here to indicate connections that are from one component on a board to another component on the board. I'm using white to indicate my clock. And yes, I could have very easily have picked up, rather than coming all the way back over here to the switch, I could have picked up from the pins off the 556 straight to the switch, to this switch here, to select which one I was actually, whether I was in run mode or single step mode. So that said, I'm not exactly sure what I'm going to do here, because I do want to create some kind of a buffer on here as well to drive these LEDs. I don't want the 556 to drive them directly, so I will probably come back and revisit that connection, or excuse me, those connections at some point here in the future. I think for now it's acceptable, and at this point this is my clock tap here. In other words, this is my actual the clock signal, and I believe I'm going to have use for an inverted clock as well, so I still need to get an inverter back in here and figure out a way to get that inverted. So now I need a buffer and I need an inverter. I'm not exactly sure which chips I'm going to select for that. There's a whole conversation we can go into related to how to buffer and how to invert. And I believe that farther down the road I may end up doing something similar to what James Sharman did on his clock later in his build, which was to actually create some state in his clock so that he could actually could control it somewhat through software as well. So rather than halting the clock like Ben Eater did James instead was able to create a software breakpoint in his code. And I like the idea of being able to do that so that I can run to a certain part, have it automatically break, and then I can single step after that. Now, Ben Eater also went through the effort of debouncing this using another 555 timer, but he kind of cheated a little bit. He just used the SR latch, set reset latch, in that 555 timer. And I can very easily do that with a NAND gate or a NOR gate. There are quad versions of each of those that I could use to create that same state and not have to use a 555 or a 556 for that particular connection. If I do that, then getting the inverted clock is very easy because I can use a NAND or a NOR also as an inverter. So that also becomes a little bit easier, but I still need something in order to drive these LEDs. And that is probably going to end up being a line driver just so that I can keep the LEDs off the actual circuitry. I would like to have them somewhat isolated by a buffer like a line driver or something similar to that. So now how do I confirm that this is actually working, where when I push the button and the timer comes on, that it's actually lasting longer than I can push the button? Meaning, how do I ensure that I'm not getting bounces here? Well, I think I'm going to have to get the scope out in order to confirm that. So let me do that. I will need likely, I guess the glare is not too bad there. So then this is my blue trace, and I'm going to put the blue trace in here right where the ground would be, and I'll ground that. So remember, it's pulled high through this pull-up resistor here. So I'm showing a 2 volts per division here, and I'm sure you can barely see it here. There are 2.5 divisions here. This other lead, which is sitting underneath it, this other lead I'm going to hook up right here where the LED is. And so therefore, when I push this button, I'm going to see the blue trace come down to low, and the yellow trace goes up to high, and then returns back, flip-flops the other direction. So I just double check my trigger here. Want the falling edge of the channel 1, which is the yellow trace. So when the yellow trace comes back down to 0, that's when it should be triggering. So now the question is, slow this down here. Let me get, so there's 100 milliseconds, and you can see I push the button and they appear to be the same length of time that I'm holding the button. And that's fine. But if I come up to, say, 10 milliseconds, if I am able to get this to hit, you can see the blue trace, if it's fast enough, and it's very difficult to do this fast enough, but there were a couple of times where it was fast enough that the blue trace of me releasing the button was separate from the yellow trace of that of the actual clock cycle, which is debounced. Okay, so that's working exactly the way as I intended it to. In the next video, I want to finally finish off this clock module, at least the version 1 of this. I'm very aware that it's taken 6 videos just to get to this point where I can start building other components and tie them into the clock. At this rate, it's going to be like just about every other one of my projects. I expect it to take about a century to complete. But for the next video, I will work on the power supervisor and adding that back in, getting an inverted clock signal, and some buffering for the LEDs for the clock. There's going to be some interesting conversations around that and how to actually go about implementing that. Time permitting, we'll talk about decoupling capacitors, and if not, that'll be next up in a future video. Thank you. See you soon.